And so here is that second problem. They're asking us to solve and graph an absolute value inequality. Now this is a seemingly innocuous little problem, but is actually one of the more terrible teasers this semester. To safely bring this home, you have to negotiate a lot of hurdles, a lot of details. Once again, I'm going to use this idea that inside every complicated problem, a simpler problem is waiting to escape. Fortunately for us, the first move is taught the same in every textbook on earth and lends itself to the idea of letting that simpler problem escape. The first move is always to isolate the absolute value. In other words, I want to get this by itself. And I can do that clearly by subtracting 5 from both sides. And when we do it, we end up with this. Now there's a reason why the first move is always to isolate the absolute value. And that's because you need to train your mind to trap for two situations that can arise at this moment in the problem. Let's just suppose that we isolated the absolute value, we ended up with one of these two situations. Again, this is pure supposition. Here we have the absolute value of something greater than negative 11. I'm hoping that you see that this immediately has infinitely many solutions. And the reason for that is because the absolute value of anything is always going to be 0 or greater than 0. 0 or all positive numbers are going to be greater than negative 11. And so x in this case is all real numbers. Now the second idea is the complete opposite of that one. This left side is always going to be 0 or positive, and 0 or positive will always be greater than negative 11, not less than negative 11. And so x here has no solutions. And so these are the two cases that you need to trap for. One in which you have infinitely many solutions, and one in which you have absolutely no solutions. That's why isolating the absolute value becomes a critical first move. So let's return to our given problem here. Key off on the fact that it's absolute value inequality. That means there's going to be two paths to solution. As simple as this seems, it's actually a lot more complicated. Now, I'm going to allow that simpler problem to escape by doing a little bit of cover up and then thinking about what works for what I have covered up. And what I usually do here is I create a number line to help me get home on that. And I've already shown here in red what works. Let's just verify this. I'm saying that anything greater than 6 but not 6 will work here in this green box. Take any number from this side over here. Is 10, the absolute value of 10, greater than 6? Of course it is. I'm also saying that anything less than negative 6 will also work in this green box. And for instance, negative 10. The absolute value of negative 10 is 10, and 10 is greater than 6. Let's be very clear here. Whatever under this box, this is what's under it, has got to be greater than 6 or less than negative 6. And that's the moment when I translate away from absolute value. Whatever under that box, in this case 2x minus 2, has got to be greater than 6 or it has to be less than negative 6. And lo and behold, I've translated this problem because we no longer have absolute value involved, just two simple inequalities connected by the logical connector or union. Now this is simply solved by adding 2 to both sides, and when I do that I get 2x is less than negative 4, and at this moment in time I'm ready to divide both sides by 2. Keep in mind that if I was dividing instead by negative 2, I would have to reverse this inequality. So that's another moment when things could go in the weeds on you. Divide both sides here by 2, and that takes care of the left inequality. The right inequality is going to be solved by adding 2 to both sides, and then again dividing both sides by 2. And when we do that, we end up with x is greater than 4. Now, in the original problem, they asked us to graph the solution on a line and find interval notation. So I went ahead and graphed it on the line. X is greater than 4 looks like this. I use the left parentheses because I'm not including 4. And x is less than negative 2 looks like this. And again, I'm using the right parentheses because I'm not including negative 2. The nice thing about doing the line graph first is it makes reading off the interval notation really quite easy. And here's what that looks like. And so I have replaced the connector OR with the union symbol. And that's pretty much the end of the problem. Really quite involved, as you can see. From such a simple beginning, there is so much complexity involved. Now, one last thing about checking these. Notice that these numbers in here shouldn't work up in the original problem. And notice that 0 is between -2 and 4. So I'm going to just show that the inequality proves false when x is equal to 0. So when x is equal to 0, this is going to vanish. I have the absolute value of -2, which is 2, plus 5, which is 7. So the left-hand side evaluates to 7, and 7 is not greater than 11. And so that's why all these numbers in here are not part of the solution. And of course, I could check it with a number greater than 4 or a number less than -2. And as you can see, checking is a really good strategy on these because it is so easy to goof up. Okay, I hope that helps.